So just with a little bit of brief idea, we had studied about extrinsic semiconductor. The word extrinsic itself means X means some external material has come. So an extrinsic semiconductor is a intrinsic semiconductor. I'm writing as SC. Intrinsic means, you know, pure germanium or silicon. And with this we add something which is called a dopant. Okay. And what is a dopant? A dopant is an impurity. And when you add this dopant, then this process is known as doping, and it's an intentional process. It's an intentional process in which you add an impurity to increase the conductivity at room temperature. Otherwise, at room temperature, my intrinsic semiconductor is almost at room temperature, or you can say at zero temperature or room temperature, it is almost behaving as an insulator. It's of no use to me, right? Now, obviously, try thinking, if you want to operate a music system, or if you want to operate a radio or a television, you obviously will not put it inside a blast furnace to get it operational. So that intrinsic semiconductor for use for making devices is of no use for us. So for that purpose, we need to increase conductivity in it, improve its conductivity with relation to temperature. We will add something which is known as an impurity, and the impurity is known as dopant. Okay. Now look at silicon, or say germanium. We'll talk more about silicon. It is in group 4. So you are bringing somebody from, say, some other class and making him sit in your class. Obviously, if you are, say, grade 7 boy, you can't bring a grade 12 boy and sit in your class. So you'll have either a grade 6 boy or you'll have a grade 8 boy. So the impurity that comes in comes from either group 3 or it comes from group 5. Okay, sorry. It will come either from group 3 or it will come from group 5. If it is coming from group 3, it has 3 valence electrons. So the impurity will be called as a trivalent dopant. And examples of this will be boron, aluminum, and indium. Okay. And in group 5, we will call it as pentavalent dopant. Pentavalent, that means 5 valence electrons. This has 3 valence electrons. I'll take this chapter like a nice story, remember, so that more questions that come on 1 mark, 2 mark, you'll be able to answer that. So it's a 5 valence electron, it's a pentavalent dopant, and pentavalent dopants are usually arsenic, antimony, and phosphorus. Phosphorus is just next to silicon. If silicon's atomic number is 14, phosphorus is 15. Phosphorus will be 1s2, 2s2, 2p6, 3s2, 3s, 3p3. This is 3p2, this is 3p3. Okay, fine now. This much story is clear. And the doping is done in parts per million, like 1 atom per million atom. So from here, 2 questions that you should be knowing, or the questions that you should know from up till this is, distinguish between intrinsic versus extrinsic, a typical question. You can also get a question like, what is doping? Then you may be asked about dopants, type of dopants, and dopants are used in what type of dopants are there. These are questions that you can get from this section. I don't think anything is left out. Yeah, no. Chale? So we begin our class today, and we begin our class with something called N-type semiconductors. N-type semiconductors. Okay, children, we started our story from conductors, semiconductors, insulators. Then we threw apart, just like a rocket launch, we are throwing apart one rockets. Conductors and insulators were disengaged. We went with semiconductors. We went into pure form of semiconductors, which we call as intrinsic semiconductors. We found that that's not much of use for us. But the concept of valence band, conduction band, energy gap all remains the same. And the energy gap for a semiconductor is less than 3 electron volt. Remember that in semiconductors, there is one nice thing, that even electrons in the valence band can also conduct. Okay, as long as there is a broken pair between an electron hole, you should know that also. Like now, after that, intrinsic semiconductors we have shed off. Now we have gone to extrinsic semiconductors. Now with extrinsic semiconductors, we're trying to see what is N-type semiconductors, so that you don't forget later on. N, there is no physics out here. N is analogous to negative, ये याद रखना, and negative is analogous to electrons. This you will need. This is just an anecdote to remember. Okay, now let's look at the structure of silicon. Okay, let's look at a silicon atom. So let's say we have an atom of silicon. So an atom of silicon has got 4 electrons. Okay, so let's have one more atom of silicon out here. 1, 2, 3, 4. And let's have one more silicon atom out here. 1, 2, 3, 4. Let's have one more silicon atom out here, which has got 1, 2, 3, 4. And one more silicon. 1, 2, 3, 4. More silicon. 1, 2, 3, 4. Right? The usual bonding that will happen between silicon is that they will form covalent bonds. यहाँ पे covalent bond form होगा, यहाँ पे covalent bond form होगा, यहाँ पे covalent bond form होगा, यहाँ पे होगा this, and obviously these will form with their neighboring ones. This is a covalent bond. This is a covalent bond. This will form with the neighboring. This with the neighboring. This with the neighboring. This with the neighboring. This, and this. Hope you have understood this, right? Now, when you are bringing a pentavalent dopant, okay, sorry, let's first talk about pentavalent dopant. Pentavalent dopant. And my pentavalent dopant can be a phosphorus. Now, phosphorus has how many electrons? 5 electrons, okay. Phosphorus has got 5 electron, pentavalent, okay, right, 5. So, one minute, huh? Yeah. So let's try and see the structure now. So I have a silicon, I have another silicon, I have another silicon, and say I have a silicon out here, I have a silicon out here, I have a silicon out here. And you have introduced one fellow called phosphorus out here. Now phosphorus has gone inside. Now what happens? Phosphorus has come with 5 electrons. Okay, mind you, phosphorus has come with 5 electrons. So let me just spark 1/5 electron out here. Okay, and if you see the bonding now, silicon, silicon, silicon. Now this is more important. Just see at the center. The rest all you understand. There will be a bond here, here. Have you understood? So a pentavalent dopant comes with 5 electrons. And if I split this 5, it is 1 electron and 4 electron. These 4 electrons pair with the 4 electrons of silicon. These 4 electrons pair with the 4 electrons of silicon. Understood? Leaving one electron extra. Now, this is that particular 1 electron extra. Are you understanding the logic? It leaves 1 electron extra. So when an extrinsic semiconductor, so we'll just write down here, when an extrinsic semiconductor, this is just for definition, extrinsic semiconductor is doped with a pentavalent dopant or an impurity, the resulting semiconductor is known as a N-type semiconductor. And children, I'm just trying to write it here if it gets confused. This is an extra electron. This extra electron remains loosely bounded to parent atom. Loosely bounded to parent atom, which means you can consider that this is almost a free electron. It is a free electron. Try to understand the mapping, right? See what all I wrote? You understood this? This is when the impurity has come up. 4 electrons get paired up. 1 electron is extra. This electron is loosely bound to this parent. It is almost like a free electron, right? Another thing that you need to remember here, children, is that this sort of a dopant is known as a donor impurity. Why donor? Because it donates electron. है ना? Logic समझ में आ रहा है? Arjun, clear now? This is known as a donor impurity because it is donating electrons. This is known as a donor impurity. So what is the story? I have a extrinsic semiconductor. So an extrinsic semiconductor, we would see, don't write like this, that extrinsic semiconductor. Extrinsic, it becomes when you have doped it. You should not write extrinsic semiconductor doped with. So we'll say an extrinsic semiconductor which is doped with. Extrinsic means you are already doped, but you have doped with what? Pentavalent. Or you can write intrinsic semiconductor doped with. That is also a better word. Don't write extrinsic plus this. Extrinsic होने के लिए external item has to come. ठीक है? Shall we go ahead? Some more things. Now our interest will be all on that electron, the free electron. That particular free electron has energy very close to conduction band. मतलब इंटरेस्टिंग देखो, वो जो फ्री इलेक्ट्रॉन आएगा ना, it will not sit in the valence band. Its energy is very close to the conduction band, and that means very less energy is needed to excite it and push to conduction band. And if you want exact thing, then for silicon it is 0.01 electron volt. Yeah, it should be, just check it. Yeah, 0.01 electron volt. And for germanium it is in the range of 0.05 electron volt. Whereas if you try to see the conduction band and valence band of typically say silicon, right, this is VB, this is CB, and we knew that this is much less than how much? 3 is the standard. This is much less than 3. The energy gap in case of silicon is close to 1.2 electron volt. This is very less. That, yeah. No. Acha. Okay. I think I wrote it. Okay, fine. Sorry. So this is 0.05, this is 0.01. Thank you. Okay, that means the new energy state would be something, this is called E0. And all this is at a temperature greater than 0 Kelvin, where E0 is your energy level of free electron. Ab maza dekho. Look at the beauty. The free electron has come, and it has come with an energy which is almost close to conduction band. It is not yet in conduction, but now you can ask me a question that, sir, you said that in the forbidden gap no electron can be there. No, the electron is not there. The electron will be residing somewhere in valence band. But this is the, there are two things we are trying to show here. This is the energy index. The electron's energy index is almost close to the conduction band. Means from valence band, if you give small energy in the range of 0.05, straight away it will jump out there. Is this clear? No, it's not remaining in the valence band. That's what I said. It's at room. The energy at room temperature is enough for it to go. That's what I said. At room temperature, it has already gone there. It's not remaining. But if you actually measure it, see, when water boils, there are some molecules which will be right at the surface, some which are at the diffusion state, some which have just crossed over. But everything, the whole pond doesn't dry up when it evaporates, because there have to be some molecules which gain sufficient kinetic energy to cross over to the next state. It is like that. Okay? Nobody has seen all these things. This is the best analogy fit for us to understand, and things are still happening according to this analogy. So we say when we have a intrinsic semiconductor plus a pentavalent impurity. Okay, intrinsic semiconductor plus pentavalent impurity. Then at conduction band, children, this is what is important. At conduction band, if you look at the number of electrons are contributed from two sources. One is the electron hole pairs from valence band. Originally, that recombination is going on, or rather, I should say the word electrons generated intrinsically and electrons donated by dopant. And if you look at valence band, then the count of holes is only because of holes generated intrinsically. Now understand one more logic out here. Now if this was say 100, this is also 100. You're understanding this? These are intrinsic generation. We told you now that in a semiconductor there can be one combined bond. Assume that there is one combined and one non-combined, and then you're giving energy. So the electron moves to go and fill up the vacancy. Once it fills that vacancy, creates another vacancy. So this one and this one will be equal in 100, and 10% will be coming from these dopants. But this 10% are also huge number of atoms. Are you understanding? So as temperature increases or conduction increases, the electron hole pair combination goes on forming. Now try to understand, and then you will write. Okay, please understand. Once I have put a pentavalent dopant, I have actually increased the number of electrons. The electrons, the balance has been disturbed now. Is this understood? If you get an electron out here, you will have a hole also out here. But there are some electrons which have come from the dopant. Okay. Now as conduction increases, whenever conduction will increase, what will happen? Electron hole combination will keep on happening. Once holes are created, electrons go and fill the holes. So hole count will keep on falling, and electrons will go and diffuse into the holes. The hole count will fall. So who will be the majority charge carriers? Electrons will remain as the majority charge carriers. So we say here that in an intrinsic semiconductors, the count of electrons is sufficiently more than the count of holes. You can write down, when conduction electron increases, write down, when conduction electron increases, combination probability with holes also increases. See, understand and write. When conduction electrons increases, more electrons are now seen here. More are the electrons out here, more will be the holes which will be. See, this is an energy back band diagram we are drawing. Ultimately, all electrons are at one place only. More is the number of conduction electrons, more holes will be, electron hole combination will take place. As conduction electron increases, possibility of electron hole combination also increases. Thereby, the count of hole falls. Thereby, a fall in the count of holes. Thus, semiconductor plus pentavalent impurity, electrons are majority charge carriers. Electrons will be known as your majority charge carriers. If you have written, then let me know. We'll have a quick recap before we move to P-type semiconductors. Now you remember why I asked you to keep this thing in mind. N stands for negative, negative stands for electron. मतलब इस type के semiconductor में electrons की count ज़्यादा होती है. The more number of electrons will be there, and they are the majority charge carrier. See, let's. Have you written it, Neha? Please finish it. Then we will discuss. Conduction electron increases, possibility of combination of electron hole pairs also increases, thus holes will actually reduce, and if holes keep reducing, then electrons are more in count, क्योंकि ये imbalance तो पहले ही created है. Okay, written. Now start. Let's understand once again. We knew about intrinsic, we knew about doping. Now we are seeing the feasibility of what happens when a semiconductor, an intrinsic semiconductor, is doped with a pentavalent impurity. A pentavalent impurity comes with 5 electrons in its valence shell and comes and sits inside, where it goes and sits inside a silicon crystal. In a silicon crystal, all the silicon atoms have got 4 electrons. So out of which 5 electrons, 4 electrons go and do the job of satisfying the valency of silicon, and leaving 1 electron which is unpaired, loosely bound. That electron which is unpaired or loosely bound is almost free and is known as a donor electron. It has come from the donor impurity. A pentavalent impurity is always donor because it has more of electrons. ठीक है ना? And its energy will be very close to the conduction band. So free that if it is a silicon crystal, if giving something like 0.05 electron volt, the electron is sufficient energy to jump to the conduction band. Now, if you look at the conduction band, as the electron counts increases, the electron hole combinations also increase. And so, ultimately, holes form, holes get filled. But there are still some more electrons which are freely available. So, if we look at the conduction band, we get electrons which are generated intrinsically. Because in intrinsic semiconductor also we said, if you raise temperature, there will be this pair creation. But you also have electrons which have come from the donor impurity. Whereas in valence band, you are having only holes which are from the generated intrinsically. So if you see, the number of electrons are much more than the number of holes. So the majority charge carriers, ultimately whoever will be carrying the charge, we know that in a semiconductor, 2 currents flow, hole current as well as electron current. But here the charge carriers of electrons are more. Therefore, they are known as N-type semiconductor. So what is an N-type semiconductor? A pure semiconductor doped with a pentavalent impurity, which has electrons as its majority charge carriers, is called a N-type semiconductor. In such a semiconductor, the free electrons which come from the donor impurity have energy almost near to the conduction band. And if you want to be interested in numbers, small energy in the range of 0.05 for silicon is sufficient for those electrons to get into the conduction band. Clear? ठीक है, तो यहां से क्या क्या क्वेश्चन हो सकता है? Questions can come is, what is donor impurity? Name some pentavalent dopants. Define what is extrinsic semiconductors. What are the properties of, define what is an N-type semiconductor and what are the properties of N-type semiconductor. Ask yourself, donor impurity, you know, somebody can donate only when he has more. A rich man donates, a poor never donates, right? What do you donate? Electrons are what you are donating. See, if you see in the other way, whenever what you call phosphorus is coming, phosphorus doesn't come only with electrons, it has got 15 protons also. Ultimately they are coming as neutral, वरना आप semiconductor छूते ही shock खाओगे. They're charged bodies. It's not like that. Overall charge gets neutral, but the number of electrons is more. Phosphorus is also coming with 15 electrons, yes or no? So higher level electronics जब पढ़ते हैं, we consider that also. Clear? Shall we go to p-type semiconductors? Are we fine? Chaliye, let's go to p-type semiconductors. Now, obviously the discussion starts with our anecdotes. P-type semiconductors. P stands for positive and positive stands for holes. Means what will happen here? Now you have already got the idea. Holes will be majority charge carriers, and holes cannot be in conduction band. Holes will be always in valence band. Because how was the hole created? The electron left the place and went to the conduction band. So the hole was remaining at the valence band. So here pura kahani kahan pe hoga? Here the imbalance will be seen in the valence band. In the previous one, the imbalance was seen in the conduction band. Okay? Chaliye. So we have a semiconductor, and now we are doping it with a trivalent impurity. Trivalent impurity. So let's see the structure. Okay, so I have got silicon 1, 2, 3, 4, and I have brought a trivalent impurity which is boron. So let's say this is boron. Oh, I should have drawn it with a different color. That makes sense more. Yeah, right. So let's have boron out here. 1, 2, 3. Let's make some more silicons.
Can they ask us to draw the structure as well?
इतना मार्क्स नहीं है इस चैप्टर में. This is for your understanding, so that tomorrow when a 1 mark question or something comes, your funda is clear. So let's form the bonds. Toink, toink, toink. Not that difficult also if you try to see it. Our problem is in this zone. Okay, so let's see the arithmetic first. You yourself will understand. Trivalent impurity is coming with 3 valence electron. Agreed? I don't know, slowly my spelling mistakes have increased like 3 valence electrons, and the semiconductor is silicon which has got 4 valence electron, right? If you see out of this 4 becomes 1 electron plus 3 electron. Try and understand, then you can make your own note. I'll wait for you. It becomes 1 electron plus 3 electron, right? This 1 electron plus 3 valence electron, they bond up. Tuck, tuck, tuck. Have you understood? 3, 3, 3 bonded. Now this silicon still has 1 electron only, which is the red one that I have drawn. Don't you think that there is a hole formation out here? Yes, there is a hole. This sort of combination, have you understood the logic? This silicon, 1 electron is not bonded. You might say, sir, this is a free electron. This is not a free electron. A free electron is free only when after satisfying everything, you still have something which is of no use. This is not free. You have one extra sweet in home because your child has not yet come from the playground to eat it. After your child has eaten all the sweets, if you still have extra sweets, then that's a free sweet. This is not free suite. So it is still in hunt for, there is still a slot. एक और electron आएगा, one more child should come. This is not free electron. Have you understood? So what do you find here? You find that when you have a semiconductor which is doped with a trivalent impurity, the 3 valence electrons form covalent bonds with the semiconductor atom, which is silicon or germanium, thereby leaving 1 electron of silicon or germanium still unpaired. And an unpaired electron or a non-formed bond in electronics is a hole. Simple. क्योंकि यहां पे एक और इलेक्ट्रॉन आएगा तो ये बॉन्ड फॉर्म होगा. So this hole is like potentially like a attraction center. Electron come here, electron come here. So whenever an electron comes here, one more hole will be created. Clear na? Because we know all these things are going to happen at एक extra आपने पैदा कर दिया. ऐसे भी at room temperature there are some bonds which are broken. But you have created one more slot. Once this slot is created, some neighboring electron will come and fill this. That hole will be created. So end of the day, the imbalance has been done. So shall we write it? So please first write down that you can write down that pentavalent plus this creates, 1 minute, just write it in this manner that I have written, and then we write 3 electrons plus 3 valence electrons. This will be a covalent bond. Okay. And this will be an incomplete bond. And an incomplete bond will have tendency to accept electron, and once it has a tendency to accept electron from neighboring complete bond. Nobody will ask you question to this level depth, but if you know it, then you can answer any question. No, can accept tendency to accept electron from neighboring complete bond, and thus can be treated as a whole. So whenever you see an incomplete bond in our language of electronics is like a whole. Now we should talk also about the energy. Right. Now there was a free electron. There we had a free electron. And the free electron had an energy which was almost close to the conduction band. Here we have a hole. So an electron has to gain energy and fill this hole. Okay, so we write energy needed by an electron to fill this hole is close to the valence band energy. Or rather, we'll write this hole is defined as acceptor energy level, EA. That was E0, donor energy level. This is known as acceptor energy level, and this is just above valence band. This is just above valence band. So if you try to draw a diagram, our diagram should look like this now. This is my valence band, and say this is my conduction band. This is the energy gap, which is close to 1.2 electron volt, and the EA is somewhere here. This is EA, and again this gap is 1. the same. The energy is very less. The energy is closely in the range of 0.05 eV for silicon. So if you give 0.05 eV, then the valence electron from the valence band will go and occupy this. So let's quickly have a look at it. P-type semiconductors are to be known as positive. Positive means holes. So when a semiconductor is doped with a trivalent impurity, the trivalent impurity comes with its 3 valence electrons, pairs up on covalent bond with the 3 valence electrons of the semiconductor atom, leaving one incomplete bond. An incomplete bond is like a hole, and this incomplete bond will be filled up by an electron from the neighboring complete bond. It will go and fill this and again create a hole out there. So the energy needed by a neighboring electron to come and fill it up here is known as the acceptor energy level, or we call it as EA. There it was E0, and EA is just above the valence band. Okay. So shall I change this slide? Zoe, can I change this? Okay. So we'll write our equations again. So our equation will be semiconductor. And when you are saying semiconductor means these are all intrinsic pure, plus trivalent impurity. Semiconductor plus trivalent impurity, which is known as acceptor impurity. So this is one more question. What is an acceptor impurity? And why is it called such? An acceptor impurity is a trivalent impurity because when it comes, it accepts 3 electrons from the parent semiconductor atom rather than donating anything. So at valence band, number of holes will be equal to holes provided by acceptor impurity plus holes created intrinsically. Are you observing the difference? And at conduction band we will write at CB the electrons will be equal to electrons created intrinsically. Acha, don't try to make me happy. Now since this is your 3rd class, topics are much tougher than grade 10, right? You will automatically see it's not possible to remember everything and write. Is the way that I'm explaining you going at a proper pace, that it is entering your head and not becoming overhead transmission? Not too much of Greek. There will be Greek Latin content upfront. I'm saying my job is you should straight away puke anything that you are unable to take in. Then we will again feed you once again. But considering 20 objective type questions, do not gulp anything that you don't understand. No way. And at least read and come for the next class. Theory chapters. This chapter, wave optics, those are like that. So at electrons created intrinsically. So we write when hole count goes up, like we said, when conduction electron goes up. So when hole count goes up, and H means number of holes. When hole counts goes up, probability of combination with electrons also goes up, and this reduces electron count. So the count of holes are always more than the count of electrons, and therefore the holes will be known as the majority charge carriers. Write it down, that carriers. In case of a trivalent impurity, the hole count is always more than that of the electron count. Is your school still now going to have a full day, half day, or overall half days now? But there's some government rule for all half day. How about you, Arjun? School? Half days. Right now you're having full day, full school. DPS?
This will also be have a break between the new election.
No, has half classes started, full classes. Okay. अगर ये लिख लिया तो इसको रिवाइंड करेंगे. Oh, I didn't charge my watch today.
This is the last 2 words after majority.
Majority charge carriers. Sorry. They are anyway going to conduct. So they are going to conduct for whom? So quick recap out here. We have a p-type semiconductor. It is created when a semiconductor is doped with a trivalent impurity, 3 valence electron pair up with the 3 valence electron of the semiconductor atom, forming 3 covalent bond and leaving 1 incomplete. 1 incomplete is like a hole. Now, when this 1 incomplete bond is there and a hole has been created, such impurity is then said to be a acceptor impurity because it accepts the electron, right? And the electron that needs an energy to come here and fill this up, that is known as the acceptor energy level. How much energy does that electron need? Well, that electron needs an energy which is marginally above the valence band. So there's an immediate chance for it to come and fill up that particular hole. Now, as the energy, this number of holes go on increasing, the number of electrons from neighboring atoms go on and come on and go on filling up these holes. So the electron count reduces and the hole count increases. So we say that in this type of a semiconductor, the holes are the majority charge carriers. And if you look at the imbalance, at valence band, you have holes which have been provided by the acceptors plus holes created intrinsically. At conduction band, it is electrons created intrinsically. ये और ये बराबर होता है, ये extra हो गया. ठीक है? This leaves you to one question, which will be, I will narrate the points and you can write down. Distinguish between intrinsic and make a T format. Intrinsic semiconductors and extrinsic semiconductors. This used to be earlier a very common question. If it comes, then you're damn lucky now. So all our discussion. An N-type you write. On N-type you write. Oh, sorry. What did I write? No, not intrinsic. It is N and P type. I'm so sorry. Sorry. N-type. N-type. And this is P-type. Distinguish. Better. Both are extrinsic semiconductors. So we won't write this is an extrinsic semiconductor, this is, then it's not distinguished. It's the same feature. So we'll write this is semiconductor or extrinsic semiconductor doped with, this one is doped with what? Pentavalent. Write down. Under N-type you write extrinsic semiconductor doped with pentavalent impurity. Extrinsic semiconductor doped with pentavalent impurity. And you can write the pentavalence as arsenic, antimony, phosphorus. And for best thing, phosphorus atomic number is 15. Phosphorus is just next to silicon. 15. Again, in extrinsic you write, sorry, P-type you write extrinsic semiconductors which are doped with trivalent impurity. Extrinsic semiconductor doped with trivalent impurity. The examples are boron, indium, aluminium. Boron, indium, aluminium. Going back to your previous column where you wrote pentavalent impurity, in bracket you write with a different pen donor impurity. Pentavalent impurity means donor impurity. Yeah. Always keep one red pen with you in this class. Or best is go to Golchas and buy that multicolor pen. Zoe used to have them. We used to have one green, red, black, and blue. Yeah, that's of Hauser, I think. But that's very Motu. Pretty much annoying. So, right there, donor impurity. And in case of trivalent, you write acceptor impurity. Is this much done? So now again in N-type you write extra free electrons are provided by the impurity. Donor impurity. Extra free electrons are provided by donor impurity. And on the other side you will write extra holes are created by acceptor impurity. Extra holes are created by acceptor impurity. Maybe 2 more classes we should be done with this chapter now. So our next point was about free electrons and extra holes. Never say extra holes donated. पूरा wrong हो जाएगा. Donate word use ही नहीं कर सकते holes के साथ. Created. With holes it is always created. With electrons it is donated because hole is a concept. Understood? Hole is a concept. Okay. Third line you write electrons are majority charge carriers. Holes are minority. In the same thing. Means here you should write electron majority charge carriers, holes minority charge carriers. Why did you write for the holes also? Because next section we will study about something called minority current. Yeah, very much deep into it. Zoe is like peeling onion shell one after the other and getting inside and inside. Okay, minority charge carriers. So just write the reverse out here. Holes are the majority charge carriers, electrons are the minority charge carriers. And then you give your notation Ne greater NH, NH greater Ne. You understand and you write. And whatever time is left, we will have a discussion on PN junction. डन बच्चा क्लियर ये बढ़ के चला गया तुम्हारा क्लास टेस्ट में फुल मार्क्स आ जाएगा instead of going and again rewriting at home I'm very happy that all of you all are maintaining it properly यहीं से करके जाओ मेहनत 2 बार नहीं है after that you have your additional notes which I have given you Arjun you are able to access Teams and all right can do from there right. Our next topic is now we need to shed off these 2 things also what we have studied and we need to combine these 2 and our next topic is known as a PN junction. So what's a junction? In railway language we say if there is a main railway line going and from one particular node there is another railway line which takes you to a place and the commutation from there comes till that node and again they take the main line then that is known as a junction. So what is a PN junction? So you'll read in many books like a PN junction is formed by bringing a p-type semiconductor and an n-type semiconductor end to end face to face. Okay, but try to understand the logic first. Okay, so you will read people will say that a PN junction in many notes it will be written a PN junction is formed by bringing a p-type semiconductor and an n-type semiconductor face to face with each other. Bhai sahab, it is not like the way they say. 1 minute. Yeah. So they'll say PN junction is bringing a P type and an N type semiconductor close to it. This is not exactly, ऐसा नहीं होता है. The prerequisites are that the P and the N type should be from the same mother semiconductor crystal. Okay, so I'm just writing that the P and N type semiconductors should be a part of same parent semiconductor crystal. Okay, now before this, though not in your books, just for interest we should know, how do we actually dope? Doping कैसे करते हैं? There are two ways of doping. One way of doping is taking the semiconductor and heating it in an environment of dopants. So whenever you heat something, there will be, once you heat, expansion will take place and the dopants can come and diffuse into it. Another way is bombing a semiconductor with a stream of dopants. Then also you have ionization energy and it will just come and go and fit in that place. Now here we said, many books and notes it will be written, what is a PN junction? A PN junction is formed by bringing a P and an N type semiconductor face to face with each other, and a junction will be created out here. Your question is, where does P end and where does N end? So slowly we will see, it is not exactly like this. There will be a gap out here, which is no man's land, neither this country or that, like in borders we have. So the actual way is both the P and N type semiconductor should be part of the same parent semiconductor crystal. And then how do you manufacture the PN junction? You don't bring two together. You will actually dope one side with N, means you'll dope one side with pentavalent impurity and you will dope one side with trivalent impurity. Okay, so you take the same crystal. This is my same crystal. This is my semiconductor crystal. And in this, I will dope this side with, say, trivalent. Trivalent means acceptor impurity. And I'll dope this side with pentavalent. And if I dope this side with pentavalent, it is known as donor impurity. Right? Then the type of semiconductor that I will be getting will be known as a PN junction. So a PN junction is actually a semiconductor, pure semiconductor, which has been doped on either side with pentavalent and trivalent impurity to create a P nature on one side and the N nature on one side. अब जरा बच्चों इसको देखो तो मजेदार से, there will be certain zone created. You are doping it with trivalent. That means what will happen here? Here the hole carriers will be much more than the electron carriers. Whereas on this side, the electron carriers will be much more than the hole carriers. Slowly this will become N type and this will become P type. इसको बोलते हैं PN junction. That is what is our study all about. I'm just saying that if I start that, it will go halfway and we won't be able to complete. That's all right, because after this I have a PN junction diode and this, which can be done in one class. Right. So just note down 2 points. If you have noted down, very good. I'm just repeating. Okay. To form a PN, just listen to me. Don't write. If you have written, don't write again. To form a PN junction, both type of semiconductors have to be a part of the same crystal. Remember that. I think you have written that. Okay, when a semiconductor material is doped in such a manner that one side is doped with trivalent impurity and the other side with pentavalent impurity, we get a PN junction. Or in other words, we get a side of a crystal which is P type and one side of the crystal is an N type, and that is known as PN. In the N region, the number of concentration of free electrons is more than that of holes, whereas in the P region, the concentration of holes is more than the electrons. Okay. Now just some prelude. I don't want you to write because from here we will carry on our next class. Now what will happen? Can I say holes like positive, positive? I can write here. We have more of positive. Doesn't mean that we don't have electrons out here. We have electrons also, but the electrons are minority charge carriers. We have electrons, electrons. Electrons, this is always काल्पनिक, ये हमारा सोच है, इधर जा सकते हैं. The electron will now jump on this side. Are you understanding? Let's say, this is next class we'll see, one electron jumps to this side to fill this particular hole. Don't you think that will create a hole out here and this electron is gone? Take like this, more and more number of electrons will be going, and you see the beauty. What was this? No, this will not become P. At this junction, you know, this diffusion will happen. ये दूर वाला इतना नहीं आएगा ना, पास वाला जाएगा. This is an N-type semiconductor which will now have a majority of holes on its this side. Yes, and this one will have more of electrons on this side.
There's a part in between both of them.
Both part in between both. ऐसा होने के बाद our structure will become something like this. जो आप पहले सोच रहे थे ना, our structure will become something. Sorry, our structure will become something like this, right? I don't know where the P ends. I don't know where the N ends, but I will have lots of electrons out here, and I'll have lots of holes out here. And my child, this thing remains that this is the N side and this is the P side. समझ में आया आपको? Now, since you have not studied capacitor, this is like extreme concentration of electrons, extreme concentration of holes or positive charges. Don't you think a polarity will be set up, a field will be set up out here? An electric field is always the direction in which the electric field is direction in which the holes move. Okay, so itna holes यहाँ पे move कर चुका है. The holes have moved this side. So ultimately an electric field will be set up. Electric field will be set up. And electric field is the direction in which holes move. Means in our language it is always like this. From a positive charge, electric field always radiates out. This you'll read in first chapter. Abhi just मान के चलो. And on a negative charge, electric fields get inside. There's a positive charge, electric field idhar aayega. Now electric field is the direction in which a positive charge goes. That means negative charge should go in which direction? Opposite to the electric field. So all the electrons which came here, aa to gaya. Now slowly this electric field was zero at the start. First one came, a charge got created. Another one came, two charges opposite. So you should have a opposite charge layer created. Once the layer is created, the electric field is slowly building up, and has now become sufficiently strong not to allow any further diffusion to happen. Before that, whatever current you were observing is called diffusion current. Now this electric field will say enough. No more going and crossing it. Why? Because the electric field is in this direction. The negative charge will never go along the electric field. The negative charge will always go opposite to the electric field. Is it getting clear? फिर से देखते हैं. यहाँ से धीरे धीरे क्या होगा? Since you have concentration on both sides, electrons start jumping. The first electron comes this side. The first electron has come this side, leaving one hole. A very minute electric field will be born. Electric field is always to the negative charge and out from the positive charge. Another electron comes, another electron comes, another comes, another comes, another comes. ये electric field तो बढ़ता ही जा रहा है ना. And say you keep a charge plate here, another charge plate out here. There's a strong electric field between them. If you touch them, touch करके spark करेगा. That's what is going to happen now here. And further, this electric field will no more allow any more diffusion to happen and create one layer which will be known as, and here there won't be any charge. Neither N-type, neither P-type. And this is a very small zone, and this is known as depletion zone. And the depletion zone does not have any free charge carriers. And it will create a potential. An electric field always creates a potential difference. For example, you are at this height, a person at this height. You don't expect this person to go here. However, this person can slide and come this way. Possible. More potential energy, less potential energy, MGA. So this will create a potential difference between these two. There will be a potential difference created between these two, almost like 3 electron volt. At that potential difference, no more diffusion current can flow through. and you have depleted the layer. Depleted means a layer has been created which is devoid of any pre-charge carriers and has a potential across them. That potential is known as barrier potential. What is it known as? Barrier potential. And the zone will be known as depletion zone. But you want current to be conducted by this. Then you will give an external voltage which will be more than the barrier potential. Child is unable to jump from this part of the drain to the other part. That's a barrier. You have to motivate and give him so much strength which is more than the fear created by that barrier. Then the charge carriers will jump and this thing will start conducting. This is the policy. We read about valves, you understand? Pressure difference. So initially this will act like a lock. If you increase the potential from outside, the barrier potential will be overcome. You remember I had drawn one plate in that small RO filter. The plate is now fallen like this. Now water has to be impinged on this plate with sufficient force for the plate to lift. Then water will go inside. Conductivity will happen. That is what we will see in next class.
After the electron jumps from N to P, won't it tend to go back to the free space?
नहीं जाएगा. वो दूसरा वाला आएगा यहाँ पे. They are opposite ना. Lots of holes here. ये पे जाओ ही मत, पहले इसमें आओ. Lots of holes, lots of electrons. टक 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 जाती रहेगा.
ये खाली हो जाएगा.
कौन सा? खाली नहीं, इधर होल्स फॉर्म हो रहा है. खाली कुछ नहीं है इलेक्ट्रल. इधर पॉजिटिव चार्ज बन रहा है. What do one ghost speak to the other ghost? Hey, do you believe in men? What do two men talk to each other? Do you believe in ghosts? So ghost must be talking, do you believe in men? Are you understanding? You are seeing it from the perspective of human being. Ghost, ghost, ghost. तो ghost भी तो man को डरता होगा ना? नहीं तो दिन में निकलता. तो आप इसको पॉजिटिव चार्ज समझो. जब एक चीज पे जब पॉजिटिव नेगेटिव डिफरेंस हो जाता है, इलेक्ट्रिक फील्ड डेवलप हो गया. इलेक्ट्रिक फील्ड इज समथिंग लाइक ग्रेविटेशनल फील्ड. Do you expect there is a gravitational field in the earth? Everything is pulled towards this side. Do you expect to throw one apple and the apple will go and land in Jupiter? No. उसी तरह, once the electric field has been created so strong that now no more this thing can come here. और बीच में कुछ नहीं है. And that is known as depletion zone. And due to this electric field, there will be a potential difference created. That is known as barrier potential. Now, if you can supply potential to these two ends greater than the barrier potential, then this electric field will be defeated and conduction will happen. यही काम है डायोड का. वो आगे क्लास में देखेंगे. ठीक है? Don't lose heart. ऐसा छोड़ देने से थोड़ी होगा. इतना करके now you're on the almost at the end. Then we'll see what is the practical application